Hi, this is Anita from RMD Engineering College. I would like to discuss about basic gates and universal gates. The basic gates are AND or NOT gates. So, why are they called as basic gates? Means the digital circuits deals with these gates as a basic ones. So, what is the AND gate? This is actually two input AND gate. We can also have three inputs. The input is this side. If it is going to be three inputs, then it would be A, B, C. Here I am discussing about two input logic AND gate. That is A and B are the two inputs. Here the action that is carried out by the AND gate is multiplication. That is A dot B will be the output here Q. So that is, it will act as a switch for both A and B input. That is, if any one is 0, then the multiplication products becomes 0. If both are 1, then the multiplication products becomes 1. So for the inputs 0 0 0 1 1 0, either both or 0 or any one is 0, the output will be 0. If both the inputs are 1 only, then the output will be 1. This can be clearly explained by the switch also. Okay, so when both the inputs are 1, both are closed, then we get the output as 1. But if any one is 0, that is, if any one is 0 means the switch is open. The input cannot reach the output. Hence, it will be 0 for all other inputs as such here. Only it will have 1 for both the inputs 1. The next basic gate is a two input logic OR gate, AB. This carries out the operation of addition. A plus B will be the output Q. So here these switches are in parallel form. So any one input can be carried out at the output irrespective of the other input. So if you see the truth table, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. So for both the input 0 only, we will have as 0. For other inputs, either of them 1 or both of them 1, we get the outputs as 1. The next basic gate is NOT gate. NOT means when I'm going to give A as input, A bar will be the output. Its complement. When it is 0, it will be 1. When 1 is the input, then here we will get 0 as the output. When there is 1 as input, then the output will be 0. Complement. Here we get A bar. So here as you see, the input is 0 and output is its complement 1. Input is 1, its complement is 0. Next we are going to see about the universal gates. The universal gates are NAND and NOR gates. Why are they called as universal gates? Because using these two gates we can establish all other gates. So hence it is called as universal gates. So if you see the AND operation, let us take, actually this is the NAND gate symbol. That is AB input and the output is Q. This is the symbol of NAND gate. So this NAND gate can be used to represent all other gates. AND gate, OR gate, NOR gate, NOT gate, buffers, exclusive OR, exclusive NOT. I will tell you some of the examples here. So here to construct AND gate, what is the AND? The AND output should be, it is A dot B, that is the multiplication. This should be the output. So see how we are going to use it. Here the input is A and B. NAND. NAND means not AND. Not AND means A dot B will be the output of this stage. The output will be A dot B. So after that there is a bubble. It means inversion. Then A dot B will be A dot B the whole bar. Then again it is passed to the NAND gate whose inputs are tied up. When the inputs are tied up like this, then the two inputs are equal. So here A dot B, the whole bar is passed to this. So when this operation is carried out, then it becomes, the negation becomes cancelled here. That is, the input passes here and the negation will be carried out. That is A dot B bar the whole bar. That both bars will be cancelled and we get A dot B, which represents the AND gate. Thus we are able to represent the AND gate by means of using the NAND gate. So this is how we are using. Likewise, the OR gate. OR gate output is here. The OR gate output is A plus B. This A plus B can be implemented by means of using the NAND gate. Here the inputs are tied up, hence the A passes through this, it gets A bar, and here the input B passes through this, it gets the output B bar. A bar, B bar. When it is passed through the NAND gate, it will be A bar dot B bar the whole bar. So this will be the output here. So that is A bar B bar gets multiplied at this AND gate, and then there is a inversion. That's why I have represented like this. So this, when it is solved, we get A plus B. We can also apply the Boolean's theorem. Here dot means we can replace it by plus. Then the whole bar means individual bar. That is, we could write it as A bar complement plus B bar complement. A bar complement, B bar complement. So that's why we get A plus B. Okay. So here also we have represent the OR gate by means of the NAND gate. Likewise, we can represent the NOT gate. Here the inputs are tied up. When A is passed through this, it gets A bar. So the inverter NOT gate is represented by using the NAND gate. Likewise, all other gates can be implemented by these NAND gate. Hence it is called as a universal gate. We will see an example for NOR gate. This is the NOR gate symbol. NOR gate means not OR. We are having the OR and a negation. Okay, this is not OR, NOR. So AB is the input and the output will be A plus B the whole bar. OR gate operation is A plus B. Here one negation is there. Hence it is A plus B the whole bar. Okay, so we can represent the OR gate using the NOR gate. What is the OR gate output? It is A plus B. How we can attain this? So when the inputs A and B are passed through the NOR gate, we get A plus B the whole bar. Then again, if we pass it through the NOR gate with the input tied up, this will be like A plus B bar the whole bar again. The two negation gets cancelled and we get the A plus B as output. Hence, we have represents the OR gate with help of NOR gate. Likewise, we can represent the AND gate. by means of using the NOR gate, not OR. So here A, when it is passed through the tied up NOR gate, then this input negation will occur. Likewise, this input negation will occur. So A bar and B bar separately will be the output of these two NOR gates. Then when it is passed through another one NOR gate, the operation will be like A bar. The first is a OR gate. Till this it is OR. So A bar plus B bar, because OR operation is addition. So after that there is a negation, which is a NOR gate. So this will be like the whole bar at this point. Okay. So then this can be expanded, this can be solved by using the Boolean algebra. So here we can say it as De Morgan's theorem could be applied. Here the plus can be carried out as a dot and the whole bar can be splitted up and it can be written as individual parts. That is, A bar is the one of the variable, dot B bar another variable. So when I am going to separate like this using the De Morgan's theorem, each will have its separate complement. So it becomes A dot B. So that is the output of the AND gate. Thus we have represented the AND gate by means of using the NOR gate. Likewise, we can represent the NAND gate using NOR gate, NOT gate using NOR gate, buffers, exclusive OR can be again got by the NOR gate implementation, exclusive OR likewise. So thus the NOR gate and the NAND gate is called as the universal logic gates because it can substitute all other gates.